So welcome back onto STEM Baba. In the last video, we started with a new chapter, rotational dynamics and static equilibrium. Now there we studied about a new term which is very important, the torque. And we saw how to calculate the torque for tangential and non-tangential forces. Now in this video, we'll see the connection between the torque and the angular acceleration. Now, one thing we know that torque causes a change in the rotational motion of an object, and to be more specific, torque acting on an object causes the object to have an angular acceleration. This all stuff we're going to see in this video. So take a deep breath and relax. Okay, so let's discuss the relation between the torque and the angular acceleration. So consider this small mass m connected with this light rod of a radius r, and this is the axis about which this rod is rotating. Okay. Now this mass a force F. This is basically the tangential force. It is applied on this mass m, and this start rotating. Now since this rod is very light, so we can neglect its mass. Now according to the Newton's second law of motion, if we apply the Newton's second law of motion on this mass m, I can write that the acceleration will be equals to F divided by m by using the Newton's second law, right? And also if you recall the connection between the angular acceleration and the linear acceleration, it is A is equals to R alpha, right? And from here alpha will be equals to A over R. Do one thing, substitute the value of acceleration here in this expression. So what you'll get, that alpha will be equals to acceleration, we have F over m, right, and divide by R, like this. Further, this would be equals to F over m into R. Now I'm doing one thing here. What I'm doing here is I'm multiplying with R in the numerator as well as in the denominator. We can do it like this. So alpha from here, this would be equals to R into F divided by m R square. Now see, magic will going to happen. In the last video we studied that when the tangential force acts onto the body, the torque we have R into F, where R is the radius, F is the tangential force. So this term is nothing but the torque. And one more thing is here, mr square. Mr square is what? The moment of inertia of a mass m rotating in a circle. This is I, moment of inertia I. So what we can conclude from here, that alpha is equals to torque divided by the moment of inertia I. Torque is directly this angular acceleration is directly proportional to torque and inversely proportional to the moment of inertia I. Now if you rearrange from here, you'll get that torque will be equals to I into alpha. And we derive this expression for a point mass m rotating in a circle, but this result is valid for any case. If there are more than one mass, this result will going to valid, and in that case, when the number of masses increased by more than one, we write that the net torque, like this, net torque is equals to I into alpha. This is for the general case. Right? Now if you recall, this is force equals to mass times acceleration. This law is the Newton's second law of motion for the linear motion. Now this law, this equation is analogous to this. Here the force F is replaced by the torque, mass is replaced by the moment of inertia, and acceleration is replaced by the angular acceleration. So this result is analogous to this. Now also Let me write it in the better form. So basically, the thing that we just derived, that the net torque is equals to, we can represent like this also. This is equals to I into alpha. This is what this we call it as the Newton's second law for rotational motion. And this was net force is equals to mass times acceleration. This was the second law for linear motion, right? So if I conclude here, these are the linear quantities I'm writing here, and this is the angular quantities I'm writing here. So in the linear motion, we have the mass m. This is replaced by the moment of inertia I in when the angular quantity is there. Alpha, this acceleration a is replaced by alpha, and the force is replaced by torque. And thus your torque, net torque is mass times acceleration. So this is all analogous to each other. Now let's take few examples on this formula. So this is the first example, and this question says that we have a light rope wrapped around a disc-shaped pulley and is pulled tangentially with a force of 0.51 Newton. Now the angular acceleration of the pulley, given that mass is this, radius is this. Okay, so we have this. Suppose we have this pulley in the form of a disc, and here we have a rope wrapped around the pulley, right? Now a force F, which is 0.51 Newton, is applied. Now we need to find the angular acceleration alpha for the pulley, given that the mass is for the pulley is 2.4 kilogram and the radius r is 0.13 meter. Now to find the angular acceleration, we can use the Newton's second law for the rotational motion. So torque is equals to I into alpha. From here, alpha will be equals to torque divided by I. How to find torque? For tangential force, torque is R into F, right? Radius we have 0.13 meter. Force applied is 0.51 Newton. The moment of inertia. Now this pulley is in the form of a disc. It is given that disc-shaped pulley. So moment of inertia for disc is what? mr square divided by 2. Correct? So if I plug all these value here, torque is r into f divided by, this is mr square divided by 2. So multiplied with 2, I can write this way. R and R will cancel. This would become 2 into f divided by m into r. So we have obtained the expression for alpha. Now simply we have to plug the values to find the result. So alpha will be equals to 2 times force we have 0.51, m we have 2.4, and r is 0.13. Solve this, you'll get the alpha to be 3.3 radian per second squared. So this is alpha. Now one question for you. How would the angular acceleration change if this radius become 2 times r and other terms remaining the same? That means this mass remains the same, force applied remains the same, just this r becomes the radius of the disk. This becomes 2 times. Then how would the angular acceleration changes? This is what you have to tell. Now let's take a conceptual question. Now in this problem, we are given with these two systems. System number one, system number two. Everything is same in the system with just one change. Here, these two balls are placed at a far distance from the axis of rotation, and here these two balls are placed near to the axis of rotation. Now, our task is to tell that if this hanging block are released simultaneously from rest, then which block will hit the ground first, the left one or the right one? This is the question. Now to solve this kind of conceptual question, we're going to use the Newton's second law of motion for rotation form. Now here we can see that the net torque acting on both the pulley is same. This is the force F is applied here, and this becomes a tangential force on this pulley, and this force is equivalent to this the gravity force applied by the gravity onto the block, and same for here also. That means the applied the torque applied torque will be same. Why? Because the tangential force is same. Torque is what? F R into F. The radius for the this pulley is same. The applied force is also same. That means the net torque applied on the system is same for both the systems. But there is one change here. If you see the moment of inertia, for the first case here, the moment of inertia will be more because masses are placed at a far distance from the axis of rotation, but here the masses are placed to the near. So if you see torque is I into alpha, and from here alpha will be torque divided by I. Now since this torque is constant, so alpha will be inversely proportional to moment of inertia I, and for the first case the moment of inertia is more, so alpha will be less. For this case alpha will be less, and for the second case alpha will be more because moment of inertia is less, and thus we can conclude that the second block will reach onto the ground first, and the left block will reach onto the ground last. So what we can say, that the block on the right side has greater angular acceleration and it will win the race. This one, that the block on the right lands first, this is correct. Now let's take one more example. Now in this problem, you can see that we have a wind turbine. Now the radius for the wind turbine, the blades, this radius is what I'm talking about. This radius R is given to be 37 meter, and the moment of inertia I is given to be 8.4 times 10 to the power 6 kg meter square. Now the initial angular speed of the blade, omega naught, we can write this is given to be 1.1 radian per second. Now as the wind speed increases, the turbine experiences a net torque of 1.6 times 10 to the power 5 Newton meter. Now there are two parts that we need to solve in this problem. In the A part, we need to find that how many rotation does it take for the angular speed to increase to 1.8 radian per second. So when the final speed, this angular speed becomes 1.8, how many times the blades rotated? And this is what we have to find in the A part. Now this problem is basically a kinematics problem. If we are able to calculate alpha from here, we can use the equations, the kinematic equations, to find the rotation it took to reach this much speed. How to find the angular acceleration? Just use the Newton's second law of motion for the rotation form. So what I can write that the net torque is I into alpha, and from here alpha will be equals to torque divided by I. Torque we have 1.6 times 10 to the power 5. I is given to be 8.4 times 10 to the power 6. Solve this, you'll get 0.019 radian per second squared. Now to calculate the number of rotation, we can calculate this delta theta in radians, and then we can convert radians into rotations. So I'm using this equation, omega f square minus omega naught square is equals to 2 times alpha times delta t. This is the kinematic equations that we studied in the previous seasons. So delta theta from here, this would be omega f square minus omega naught square divided by 2 alpha. We have the final speed, which is this much, 1.8. We have the initial speed, 1.1. Alpha we have just calculated. Just plug all these value here. We'll get the omega to be approximately 53 radians. Now you can convert radian into rotation. We know that in 2 pi radian we have 1 revolution. So this would be equals to 8.4 revolution. So the blades turned for this much rotation to obtain a speed of 1.8 radian per second. So this is the answer for the A part. Now next, in the B part, we need to tell that what is the linear speed of the tip of the turbine blades after 27 seconds. Now to find the linear speed, we have to find the angular speed. So omega is equals to omega naught plus alpha times t. Omega naught we know it is 1.1. Alpha we just calculated to be 0.019. Time is, we have to find the linear speed after 27 seconds. So multiplied with 27. So this would be equals to 1.6 radian per second. Now to find the linear speed, we would be equals to r omega. R we have the radius for the blade is 37 meter. So 37 into 1.6. This would be equals to 59 meter per second. Now which is approximately equals to 212 kilometer per hour. Now this speed is huge, and this speed is an important consideration in the design of wind turbine, because greater this speed, greater will be the noise made by the turbine. So this is all with this problem. Now we'll take a final problem and then we're going to end this video. Now this would be the last question for this video. Now here we are given that a person holds his arm straight in a horizontal position that you can see here. Now the mass of the arm is m and its length is given to be 0.740 meter. Now when the person releases his arm, allowing it to drop freely, it begins to rotate about this shoulder joint that you can see here. Now there are two parts in this question that we need to solve. In the A part, we need to find that what will be the initial angular acceleration of the arm, and in the B part we need to find the linear acceleration of the man's hand. Okay. Now we're going to solve the A part first. For that, what we can use, same thing, Newton's second law of motion for rotational motion. So I can write that alpha would be equals to torque divided by the moment of inertia I. Now we can consider this to be a uniform rod of length L, and the moment of inertia is given by ml square divided by 3. Correct? Now torque would be equals to, now we can assume that the center of mass for the arm is at the center. Now the gravity force would act in the vertically downward direction mg, and this will be basically the tangential force. If you take this to be your axis, this would be the tangential force. So torque will be R into F. Now here R will be L by 2. This distance would be R, which is L by 2. So in place of R, I can write L by 2. Right? Just plug all these expressions here. Torque we have L by 2 multiplied with the force F. I we have ml square divided by 3. Now if you simplify this, you'll get 3g divided by 2l. So this is the expression we obtained for alpha. Now just plug the values to find the result. 3 times g is 9.81. 2 times l we have what? This is 0.740. Solve this, you'll get 19.9 radian per second squared. Now in the B part, we were asked to find the linear acceleration for the hand. So here this, if you see the radius, this r would be equals to L. For this point we have to find the linear acceleration. So A is what? A is r into alpha. R in this case would be L. So L into alpha. L we have 0.740 times 19.9. Solve this, you'll get 14.7 meter per second squared. Now one thing you should observe here, that the linear acceleration of the hand is 14.7, which is approximately 1.5 times the value of g, right? That means the acceleration for this hand would be greater than the acceleration of gravity. Now this thing we can also demonstrate by using a simple experiment. What you can do here is just hold your arm straight out with the ball resting on your hand, with the ball resting on your hand, and let the your hand falls downward freely. Now you'll observe that your hand falls with a greater speed as compared to the speed of the ball, because the acceleration for the ball would be the acceleration of gravity, but the acceleration for your hand would be 1.5 times the value of g, given that the length is 0.740 meter. So this you can prove at your home also. Now one question I'm giving to you, that at what distance from the shoulder is the initial linear acceleration of the ball arm equals to the acceleration due to gravity? What would be the value of r at which the acceleration a is equals to g? This is what you have to tell, right? Simply you can use this equation to find the result. You'll get the result to be 2l divided by 3, and if you put L as 0.740, you'll get 0.493 meter. So this is all with this video. Now in the next video we'll see the next topic, that is zero torque and static equilibrium. So please do care of yourself, and we'll meet in the next video. Goodbye.